Okay, so last time we proved this theorem by theorem of Benor-Cleve, which we actually showed one side. We reduced formulas to with 3 ABPs. Right, so we have shown this direction, that if you are given a formula of size S, then you can, whatever that polynomial, suppose the formula computes polynomial f, then f can as well be written as a matrix product, right, where the matrices are only 3 by 3 cross 3. The entries are very simple, they are just variables or constants, and the number of matrices is only poly S. Right, so this we did by using some matrix identities, 3 by 3 matrix identities. And guiding principle was this interpretation via registers, that there are 3 registers and they store polynomials and we work with them. So we apply some simple transformation on one of the registers and then maybe add it to the first register. So those kind of transformations ultimately give you the full polynomial f in the first register. Okay. Any questions about that? So the other part is much easier. So the converse is, you want to show that with 3 ABP can be converted into a formula, right? How will you do that? So this is just divide and conquer. So you have let's say S 3 by 3 matrices. In fact, for this argument even 3 won't be important. So you have some constant dimensional matrices, S of them. You want to multiply them, so you actually multiply the first half, the second half, and then merge, right? So it is just like merge sort. Well, but it is not as fast as merge sort. So it is basically it is this divide and conquer argument. So instead of doing the multiplication one by one from left to right, you just do it for the each of the halves and then the two results you multiply. So let the matrix product be A1 A2 dot dot AS be a 3 by 3 matrix product. So suppose we have the left product, which is A1 dot dot AS by 2, and the right product, which is S by 2 plus 1 dot dot AS. So you have these two halves already recursively solved, and you have LR. Each requires formula size. So recursively T of S by 2, right? So we are defining this size function to multiply S 3 by 3 matrices. The formula size is, let's say, T of S. So for S by 2 you have T of S by 2. But now what you have to be careful about is how will you multiply L and R, right? So A is equal to L times R, but how will you do this multiplication? Because you have this 9 things here and 9 things here. For each of, so there are 18 polynomials, and for each of these polynomials you have a matrix product. In fact, for the L matrix you have a matrix product, so which also gives you these 9 polynomials, and analogous thing for R. So if you do this multiplication in the naive way, right, so say you multiply this with this, I mean the whole row with the first column, but then that row you have to also multiply with the second column and then also the third column. So in particular this first entry, this entry, right, this you have to use 3 times. So you have computed that entry, but to get A you actually have to use a fan out of 3, right, and that is not allowed. So how do you save this? I mean, how do you make a fan out 1? Exactly, you have to make copies of this. So that will be a slight blow up. So to avoid, or directly speaking, to get fan out 1, to keep fan out 1, we make 3 copies of L respectively R. Okay, so although L we have computed as a single matrix product, we will make copies of it. So we'll have first copy of L, second copy of L, third copy of L, and whenever I want, let's say, this first entry of L, I'll use it first time from the first copy, second time from the second copy, and third time from the third copy, so that the fan out everywhere is 1. Okay, it is not being reused. So essentially every time it is being, the computation is being redone. Okay, we are not reusing computation, we are actually repeating it, but it's only 3 times, so you have 6 of these. So this gives the following recurrence, right? So Ts is at most, so how many times T of S by 2? 6 times. And how much of size are you investing right now? Assuming that L and R are given and the copies have been made, so how much extra gates are you adding in your formula to compute these row column inner products? Constant. It is just a function of 3, right? So what is the solution of this recurrence? So it is worse than merge sort. It is not S log S. It is right. So this is S to the log 6. Which is certainly subcubic. Okay, but that is not very important. So Ts we have gotten to be poly S, right? Ts sized formula for A. So yeah, so the formula you get is just by divide and conquer and do it with some care, so that the fan out remains 1. So circuit was direct, but formula needs this trick of copying. And where are you using the fact that it's constant width? Yeah, so the copying is the only place where you need constant width. Right, that's the important point. So because of copying, we get formula size. In general, you will get, when you are using W cross W matrices, then this will give you S to the log W, log 2W. Okay, so up to constant width this is fine, but when the width is non-constant, then it gives you a quasi polynomial sized formula, right? So this at the same time we have shown that ABP model reduces or has a quasi poly formula. Okay, that is one thing we have shown. The other thing we have shown is that the model formula and constant width so formula, whatever a formula can compute, constant width ABP also can compute. It's exactly this, they are exactly equivalent up to poly blow up, poly size blow up, right? So this is an interesting fact because this ABP model and formula model were defined in a very different way. In fact, they had no relationship whatsoever. In ABP, inherently you are reusing computation a lot, and in every level actually the fan out is equal to width, and then the length can be arbitrary. So the reuse is happening in an arbitrary way, but still you can get a formula out of this. And what is the relationship between formulas and circuits? Yeah, so formula seems to be well, it is in fact no, well, okay. If you look at low degree polynomials, then it is not clear whether formulas and circuits are different. But intuitively, they seem much weaker than circuits, low degree circuits. But we don't know whether they are separate. So just circuits is strictly more than formula because, well, the degree can go to exponential. But if you restrict to low degree circuits like VP, then we don't have a good understanding of VP comparing with VF, how small or whether they are equal. And but one type of circuits are actually subsumed by formulas, which is constant depth circuits. So constant depth circuits are actually subsumed by formulas. Why is that? Yeah, so just look at depth 3 for example, right? Depth 3 is a powerful model, depth 3 circuits, but it's also a formula because nowhere do you need fan out more than one. I mean, there are these product gates and you can just make copies of everything. So you don't really need fan out more than one. So a depth 3 circuit is naturally a formula. I mean, also when you write down on paper, you are actually writing it in a single line. So nowhere are you using previous thing multiple times, previous computation. So it is so in the same spirit, constant depth is also, you can implement it as a formula. But whether you can implement formula in constant depth, that is obviously too much to ask for. We only know that formulas can be reduced to log depth. We don't know sublog. But it should be easy to rule that out, right? Just by degree. No, just look at the degree. No, but the fan out then, the fan in can be more than 2. So a product gate can increase degree by taking lots of inputs. Yeah, so this is also an open question. So these are all open. Their strictness is an open question. Right. So now we have studied several models, and correspondingly we have several complexity classes, and we have uh, some highly non-trivial relationships. Okay. It needs a lot of algebraic and algorithmic ideas. Okay. Right. So that was WIT 3. Any questions? Then we will move to WIT 2. Okay. What is WIT 2 good for? So that is also a QASM. Okay, just like depth 3 circuits, width 3 circuits, width 2 is also a QASM. So it is, although the width has been minimized, still the model remains quite potent. Okay, you can do powerful things in this model. So we will now show that even triangular 2 cross 2 matrices give a strong ABP. By the way, where did that reduction use width 3? Why was 3 by 3 matrices important? Can you do it by just 2 by 2 matrices?
The product thing might be because the sum comes directly.
Yeah, exactly. So sum actually will work. Yeah, sum is only using this much of the matrix, this part of the matrix. So sum works just like this, but product is more complicated. Yeah, in fact, there is a result by Allender and Wang that this model is incomplete. So even existentially in this model you cannot compute certain polynomials, no matter how long the ABP. So there is a result by Allender and Wang. WIT 2 is an incomplete model. So for example, so can you think of a polynomial that is a good candidate? Impossible to compute here. So since addition can be done, so somewhere you have to also multiply things to make it difficult, to make it hard.
How far can we go with the degree? Like,
Yeah, so the degree actually is, it will be quadratic. There is a quadratic polynomial that this cannot compute. So like x1, x2 plus x3, x4 is what you can try first. But this probably has a WIT 2 ABP. So keep going. It's go up to 16 variables, and then you get Allender-Wang's proof. Okay, so there are these. It's a 16 variate and 8 monomials. They are all disjoint monomials, and WIT 2 model is just cannot compute this. It's impossible.
so is this proof just by counter example?
Right, right. I mean I guess no. So guessing a counter example is not so hard, but you have to prove that this doesn't have a WIT 2 ABP with unlimited resources, unlimited length. No, no, I will not do it. I don't think it is that hard actually. You just have to go this modulo, go modulo x1, modulo x2, and so on. Because in a with 2 ABP, your matrices have just linear polynomials, right? So actually you can go modulo those linear polynomials so that your 2 by 2 matrix becomes triangular, and then show that this polynomial on the left hand side, this polynomial f, under the modulus you get some contradiction, because this is also absolutely irreducible, right? This polynomial is clearly irreducible, and try to use some modulus operations to get that contradiction. So this I will not do. Yeah, I'll see how difficult it is, and then it can become an assignment. I don't think it is that difficult. Okay. So let me get back to, well, so WIT2 by itself is generally speaking it is incomplete, but that doesn't mean that it cannot compute hard polynomials, right? So maybe it can still compute some hard polynomials, and that is what we will show now. There is a result by Saha, Saptarishi and me, which shows that in a way you can convert depth 3 circuits to WIT2 ABP. Be a sigma pi sigma polynomial, n variate. So let's also add that here. N plus 1 is the bottom sigma Fanon. K is the top Fanon, and D is the formal degree of your sigma pi sigma circuit. Right. So then there is a size not much bigger than this. So just size dk square with 2 ABP that computes, well, can we say that it computes F? We cannot say that, because, well, sigma pi sigma is a complete model. So, and just the previous counter example, you cannot, it has a sigma pi sigma polynomial circuit, but it cannot have a with 2 ABP. So what we will say is some multiple of F is computable. F times L is computable. Okay, where L is not too difficult. So where L is just is a product of non-zero linear polynomials. And even these linear polynomials will not be magical. They will just be these linear polynomials that you see in the sigma pi sigma representation. So sigma pi sigma representation is basically a sum of product of linear polynomials. So the set of these linear polynomials, you take a suitable product of them, that is L. So F times L is something that has a very small with 2 ABP. Okay. Although F may not have a with 2 ABP. In fact, these 2 by 2 matrices will also be upper triangular. So it will be a very simple representation, the simplest possible that you can think of. Right? You cannot go below with 2, because below with 2 you are just multiplying linear polynomials. Even in with 2 we are only using triangular matrices. So there are 4 places, we are only using 3, which means that this is the minimum matrix product where you have non-commutativity. Right? If you just use the diagonal entries, then it would be a commutative product. So this is the first place where you actually have non-commutative product. That is enough to compute kind of depth 3. Is the statement clear? So yeah, let us prove this. So let F be this K products. where Pi is product of linear polynomials, D many, yeah, so I mean unsurprisingly this will be an inductive proof, uh, and surprisingly it will also be a divide and conquer proof. Okay, so we'll somehow use divide and conquer here. To be precise, we will use it on these addition. There are k product gates, so we'll compute the first k by 2 as with 2 and the second k by 2 as with 2 and combine. So base case is Pi. So how do I express Pi as a product of 2 by 2 matrices? So for Pi I will do this. Kind of the obvious thing that yeah, Li1 dot dot Li d minus 1, right. So in the top left entry you have computed almost the product Pi. But in the end I will add something different, which is this. Okay, so what is this product? So I get some Pi prime, Pi 0 1, where Pi prime is almost Pi except LID is missing. Right. So I have located Pi here. I mean, we could have taken LID also the same way as we have taken LID minus 1, and we would have gotten the product Pi, but that representation will not help you in doing addition, because remember you have to add P1 with P2 using matrix product, right. So for that you have to do something more complicated. So let us see how will this representation help. So we now need to express P1 plus P2 as a matrix product. Right. So what do you do? So well, we will not really express P1 plus P2, but we'll get some multiple of P1 plus P2 as a product of 2 by 2 matrices, assuming that we have a representation for product of P1 and a representation for product of or multiple of P2. So let us go to the next. So suppose we have iterated matrix multiplication expression for multiples of two polynomials G and H. Okay, these are some arbitrary polynomials, and the representation we have is, suppose this. Okay, so the multiple is by L2 here and by M2 here. Okay, so instead of computing G and H exactly, we have computed them up to these multiples. And L1, L3, M1, M3 are garbage polynomials. We don't care about them. So now using these two matrices, can you get, by doing matrix product, can you get multiple of G plus H? So try getting G plus H as follows, right? So what are the things that you can do? Well, you can only multiply matrices. So you have these two matrices. Let us write them. And maybe you can introduce a third matrix in the middle, which is yet to be fixed. So let us say this.
Somehow get like L2 M2G and L2 M2H.
Right. Correct. Yeah. So this you have the, basically you have L2G and you have M2H. So a useful combination of this would be M2 L2G plus L2 M2H, because from that L2 M2 will come out. Yeah, so that is exactly what you want to do. So for that you have to scale these matrices simultaneously. The scaling should happen. So for that I have introduced A and B, okay, which is yet to be fixed. So let us look at this product. What is this product? So let me directly write it. It is just L1 M1 gets multiplied with scaling. This 0 remains. Well, because you're only multiplying kind of upper triangular, three matrices. So you will get an upper triangular product. L3 M3 gets scaled. So this is the garbage part. The interesting part is what you get here. Okay, so that will give you an idea for A and B. So what should you pick A and B as? Making these equal. If you make them equal, then it's a multiple of G plus H.
This middle matrix will have elements only at the diagonals. Like before even proceeding, what was the intuition behind multiplying it with a matrix with just diagonal entries?
Just have to scale the first matrix by M2, the second matrix by
B is scaling L2. L2G is scaled by B. And simultaneously A is scaling M2H. And you want things to be as simple as possible. So we actually pick a scalar matrix. It's a scalar. So this suggests that take A to be L2 M3 and B to be L1 M2. And that will give you L1, L2, M1, M3, L1, L2. So we are only interested in this part, and that is giving us yes, but we also have to see whether for this middle matrix we have a matrix product, right? So why do we have that? For this AB matrix, do you have this with 2 representation?
if you assume at all points. If you assume at all points that these LIs are just a product from.
So answer will be very simple. Yeah, so the answer for this will be very simple. Actually, this Li, Mi's will all be just product of linear polynomials. So this middle scalar matrix is actually just naturally it factors. You don't need to design a with 2 ABP. It's a scalar matrix, and it will completely factor into matrices with which will also be scalar, of course, and they will have linear entries. Yeah, so that essentially it finishes the proof. Right? You just have to calculate the blow-ups, that the blow-ups are under control. That will happen by divide and conquer. So now basically at this point you should observe that to compute g plus h, so adding two things will be kind of doubling the size, because you are multiplying so many things, L1, L2, M2, M3. So in fact kind of 4 times. There is a blow up of up to 4 times, and so you cannot afford this blow up more than log many times, but which is fine because you can add things always this 2 at a time. I mean this. So when you have P1 to Pk, you add recursively the first k by 2 things, the next k by 2 things, and then add these two. So you will again get a recurrence with a halving. So all the things will be fine. So the size of IMM has increased.
You should add it then.
You
Okay.
get linear, right?
Sorry?
TS is 2TS by 2 plus ordered 1, something like that.
No, the exact expression we will see. What is your general question?
Exactly what he's saying. You still have to add k times, right?
S times, that
Or
solution will be
span
like
it many
S.
times.
No, this recursive steps will only be log k many times. First k by 2, next k by 2, and then merge.
So that is like TS is 2TS by 2 plus some order 1 for adding them, right?
Plus, yeah, exactly.
So,
one.
but if you have 2TS by 2, that means you
2
need
TS
to
by 2,
go
right?
to the log S many times. So that is like S.
Okay.
So but you want log S, right? Something like that.
No, what your t is the size. If your size is coming out to be poly, then you are fine. By a multiple of 4. So max increase is 4 times in one step of this. So we apply this recursively to sigma pi log k many times. So in log k additions you can get to k additions. Well, not log k additions. So in log k steps you can add k things, or log k is the depth of your recursion tree. Right, so this gives you, so we get an IMM of length so initially we had multiplied d things to compute P1, so that is length d already taken consumed, and after that you are doing it a blow up every time of 4, maybe up to log k plus 1, right? So this gives you order dk square. That's the length. So you have dk square many matrices, 2 by 2. Each matrix has linear entries and it is upper triangular. So it looks, this IMM looks like L prime L prime prime L times F 0, where L is a product of some number many linear polynomials, right? That's an invariant. So how many linear polynomials do you multiply in the end in L? I want to say dk square. Yeah, so maybe dk is too less. Dk square many. Yeah, because L2 M2 we have blown up. I mean L2 we have blown up 4 times kind of. Hmm. Yeah, so fine. So dk square is certainly an upper bound. So that many linear polynomials we have multiplied. That forms this cofactor L, and L times F is what you can now compute as a width to ABP. And what are these linear polynomials? So that you can see in the induction step or recursion step. So these are the I mean if you look at P1 plus P2 computation, so P1 has these
I still have a doubt regarding one step.
so what is Pi prime, right? So Pi prime has these linear factors which appear in the Pi prime and Pi are these linear factors which appear in the sigma pi sigma representation. So these are the things which you are multiplying then in a systematic way. So that gives you the multiple, right? So this is that's the full proof. Yes. Any questions?
I had a question. How do you add k things using log k many additions? Like you break it into two parts.
It's not log k additions. It is a recursive algorithm with log k recursion depth.
Okay. You just convert each of the log k times you do the addition.
No, not addition. It is done recursively, and if you look at the recursion tree, the depth is log k. So if a tree has depth L, then it has 2 raised to L leaves, and these leaves are P1 to Pk. So it is if you have P1, P2, P3, P4, then we will add P1, P2 and P3, P4, and then we will add these two things. And as you can see, this can be done beautifully in 2 depths. So these are the levels. I'm calling it 2 times, but it's not obviously 2 additions. The additions are more. So you are adding P1 plus P2, P3 plus P4, and those two. It's actually k minus 1. Okay. Any other question? Okay, so so since I don't want to start a completely different concept, or I mean which will be actually lower bounds. So the next topic will be lower bound results. This is structural results. We have done, I think, almost whatever there is to do. So the next thing will be, next family of results are either lower bound proofs. So you take a model and you show that a natural polynomial will require a very large size. Those kind of theorems. The other interesting results in the recent years are these circuit related algorithms. So some of the things which we may cover here are this PIT algorithms, so identity testing algorithms. That we'll probably see towards the end of the course. But I don't want to start it now. So I'll just continue with a recent result of WIT2, but the model will be slightly different than what we have been doing till now in the course. Okay, so it will be approximative computation. So approximative and as an example case, we will prove a result about with 2 ABP in the approximative sense, and that is written by drawing a bar. Okay, so in fact I can also do the same for formulas. So formula bar. So this bar will actually denote some kind of a closure of your model, but the closure is, I mean, at least the analytic intuition is quite complex. So instead of giving that intuition, I'll just give the explicit definition. So what is meant by approximative? As the word suggests, you don't want to compute the polynomial exactly. Right? You don't want the exact function, you want some kind of an approximation of it. So what should be the correct notion of approximation? What do you suggest?
The limit you get your polynomial.
Limit of what?
There's some, your polynomial is a function of, let's say, some t and x and so on, and then you let t tend to something.
Right.
And at t tending to something, you get your.
But if you are working in, let's say, finite field with size 2 elements, what is the meaning of limit?
I don't know.
It is a
What is the
formal
close?
variable.
Yeah, so there is definitely this analytic intuition which is being referred to, but since I want to not depend on the field, I want the notion to be independent of the field, in fact even the ring, base ring. So let me just give that definition directly. So in approximative models or computation, what we want is we compute a polynomial. So compute will now be in quotes because we will actually not compute polynomial f. We will compute something else related to f. So we will quote unquote compute f by computing something else which will be in one more variable. Okay, so we just add another variable which is epsilon, and if you have taken basic math courses, epsilon has a special character, right? It always is something very close to 0. So that we want to keep that allegiance with epsilon. So here also somehow epsilon denotes something very, very small, but formally speaking it's just a new variable. Okay, and what is the meaning of this bracket? So this is the function field, right? So it's basically ratio of 2 polynomials in epsilon. So you have now 1 over epsilon, or you have epsilon plus 1 divided by epsilon plus 2. So you have those expressions. Okay, rational functions are there in epsilon, and then the relationship with the variables x variables is the same as before. Basically constants, these are the new constants. Constants are now more complicated. Okay, and how should G behave? How will G know f? So G should be equal to f plus big O of epsilon. What is big O of epsilon? So we are actually abusing this notation, big O of epsilon, to an element in, it is a polynomial in epsilon and all the variables. Moreover, it should be a multiple of epsilon. Okay, so in algebraic terms, O epsilon is just an just an element in the ideal generated by epsilon. Okay. So basically G is equal to F modulo the ideal epsilon. But we will continue with this notation G equal to F plus O epsilon because it kind of, I mean, it carries itself the intuition that there are these lower order terms. So G is equal to F, but there are also these lower order terms which are kind of bounded by epsilon. So if you make epsilon too small, I mean analytically or real analytically, if you make it very small like 0, then G is F. Right, so this is the meaning of approximative complex computation or approximative model. So you can take any model, let's say you take circuit, you have written down a circuit that is computing G, right, which is equal to F up to higher or whatever lower order terms in epsilon. So why doesn't that mean that you also have a circuit for F? Why don't you just set epsilon to 0 and get a circuit for F free of epsilon?
Because of that field on which G is, so they can be
Right.
like divided by epsilon.
Yeah. So the only obstruction is, or only obstacle is that your circuit will be using 1 over epsilon constants, and then those things will become undefined. So circuit will become undefined. So that is the only catch here. Everything else is a triviality, right? So this definition allows us to use constants like 1 over epsilon in the model. Yet we can set epsilon equal to 0 in the end, right? So in the intermediate computation we are using a 1 over epsilon, so you cannot set epsilon to 0 because those computation things will become undefined. But in the end you get F plus big O of epsilon, and there you can set epsilon to 0 and recover F, right? So, but that doesn't give you an actual circuit because intermediate things are all undefined.
So is there a polynomial for which unless you used 1 by epsilon the circuit size would blow up too much? I mean,
Right. So whatever interesting question you will ask, we will call it an open question.
There are some, I think the elementary symmetric polynomials or something are good candidates, right? That are
So-
hard, but
Is circuit closure equal to circuit, right, or formula closure equal to formula, with the appropriate meaning of equality? We mean that if you have a approximative circuit, then there is also a small circuit, exact circuit. If you have an approximative formula, then there is also an exact formula of size up to a poly blow up, right? So are these things different or are they equal? So these are all open questions. Yeah, you had some suggestion to solve this.
not to solve.
Okay.
But so like the elementary symmetric polynomials would be like good examples. I mean, good candidates, right? But they might be hard to compute.
Well, elementary symmetric polynomials have a depth 3 circuit. It's very simple.
I mean, but the size is still. Well, you need.
No, there is a small sigma pi sigma circuit by interpolation. You just look at the auxiliary polynomial and interpolate. So you have to, yeah, so it's not clear. I mean, there is another ABP is also there. That's everything is open. So ABP bar, whether it is equal to ABP. Yeah, also, although these general questions are open, but this approximative, this concept of approximation has been used to design newer and newer matrix multiplication algorithms. So the fast matrix multiplication algorithms in the last 3 decades, they are all based on this approximative idea. Okay. So algorithmically they have been used, but it doesn't tell you anything about these fundamental questions, because I mean matrix multiplication is theoretically a trivial problem. It's solvable in cubic time. So to improve it to quadratic, approximative ideas have been used, but it doesn't tell you anything about the fundamental nature of approximation. So can circuit bar compute something that is much harder than circuits? That we have no intuition. So this is a different dimension to algebraic computation, and in this there is a recent theorem so Brinkman, Eichenmeyer and Saudam. Okay, one around 2 years old. So it says that formulas, so the complexity class VF bar, right? So approximative formulas can be written as with 2 ABPs. So any polynomial for which you have a approximative formula, you also have an approximative with 2 ABP. Yeah, with one mild assumption that you want the characteristic of the field to be not 2. Okay, so characteristic odd or 0 is fine. Over GF2, this question is still open. Okay, but I have no idea why it should, I mean, why should it not be true? I mean, it should be true for all fields irrespective of the characteristic. But the proof which they have given fails for characteristic 2. So is the statement clear? How will you even start to prove such a thing? So you have to convert formula to well, so by induction ultimately it will boil down to converting a product gate into with 2 by 2 matrix multiplication, right? So that seems to be the only thing we have to express using approximation.
We try to separate out the approximation part and the actual part,
Right.
and then for each try to.
Right. So in the, I mean, what is the benefit of approximation? It is that you can divide by epsilon. So we will actually use matrices where entries are dividing by epsilon.
You could separate out the 2 parts, then you could also probably just do it without the 1 by epsilon, right? So we probably cannot separate out the 2 parts.
No, but the other part would be the part where you're using 1 by epsilon.
So what are the 2 parts?
One where you're not using 1 by epsilon, one where you're using 1.
Yeah, but that is our definition. This F plus O epsilon is the definition.
No,
So somebody gives you,
the intermediate computation.
so here is the basic question. Somebody gives you F plus O epsilon. Can you get from this F square plus O epsilon? So this is the only thing which will be solved.
Just square. Just okay. And
No, it's a with 2 ABP.
oh, I mean, okay, in here.
So somebody gives you a matrix product computing F plus O epsilon. From that, can you get a matrix product that gives you F square plus O epsilon? So this is the only thing which will be solved here, and it will imply the theorem. Okay, we'll just show squaring. As you should know, multiplication reduces to squaring, right? Why is that?
Taking out the diagonal and if you have 10 product of matrices, take all the matrices out the diagonal, so then power it.
No, I'm talking about polynomials. There is no matrix. So if you have two polynomials f times g, if you have two polynomials f and g, then the product fg can be written as this. Okay. So unless you are unfortunate and characteristic is 2, this identity holds, right? So product actually reduces to sum of squares, and sum, nobody here doubts that sum can be expressed as with 2 ABP. So assuming that sum is easy, all we have to do is learn how to square, right? So that is all we will, where we will use 1 over epsilon. Okay, so let us, or proof sketch. So use the matrix QF. So when we think of polynomial f, the matrix version will be this matrix. It's not really a triangular matrix, but still it has only 3 entries. Okay, there is 1 0 present. So this is the matrix that will store f. Which is a polynomial in all the variables, so epsilon and x1 to xn. So if we have with 2 by 2 IMM, 2 by 2 iterated matrix multiplication expression for you have it for f plus O epsilon and g plus O epsilon. In fact, it may be for even arbitrary precision, epsilon to the k, okay, which just means that the remaining part is divisible by epsilon to the k and not just epsilon. So some precision, epsilon to the k. If you have these two expressions, then we have IIM to add. Okay, so we can add f and g up to the same precision. This is easy to guess. You will kind of just multiply the two expressions. Sorry, I should call it QF. Now we are into matrices, not polynomials. So I mean QF is a matrix plus some matrix which is a multiple of epsilon to the k. Every entry there is a multiple of epsilon to the k. So you have a representation IM for QF matrix with this error, and for QG matrix with this error. You have these two products. So if you multiply these two products, then you expect to get f plus g up to that precision, right? So that is all. With some calculation you have to show this. So there is a Q0 sitting in between. Okay, so this is just check that in the right hand side you look at QF, which is F110, Q0 is 0110, QG plus the error term, and what is the product of these three matrices? It is F plus G 110. Right, so that's the proof of this identity. So the two representations you essentially multiply with something sticking in between this 0110 matrix, and that will give you the sum. So that was not very unexpected. What will be more shocking is f square. How do you get qf square? So a trickier identity shows that if we have IMM for QF with precision epsilon cube, I mean the error terms are divisible by epsilon cube. If we have an IAM with this much precision for F, then we have an IIM for QF F square, in fact minus F square plus O epsilon. Okay, so the precision reduces, the error term is now merely a multiple of epsilon and not epsilon cube, and it is a product of lots of matrices where a lot of division is happening, 1 over epsilon, right? So that expression I will just pull out of thin air, right? So this you have to bear with me. So you want to compute f square out of this expression qf plus epsilon cube. So we will be multiplying these two, but we have to use 3 other matrices, which are sometimes some entries they will multiply by epsilon, and some entries they will scale down by 1 over epsilon. Okay, so this scaling up and scaling down with the appropriate in the appropriate places, this will lead to qf square, a q of minus f square with error epsilon. Okay, so this can again be checked. You just have to multiply the first matrix with qf, then the third matrix with qf, and then the fifth matrix. So you just look at this matrix product, this will give you q of minus f square, and the remaining things are error terms. You can check that they are all multiple of epsilon, not epsilon square and not epsilon cube. Okay, so this precision kind of reduces. So you have to start with a higher precision expression of f, and by this, I mean that you have to do because you are going to divide by epsilon. So if you started with only precision epsilon, then when you divide by epsilon, you get a whole lot of garbage which you cannot deal with. So you have to start with epsilon cube, and then it will kind of get divided by epsilon square because you have these two 1 over epsilons, right? So although there is this width 2 by 2 IMM expression, this doesn't exist for epsilon equal to 0, right? So that is the and you know that provably it doesn't exist because there is a polynomial which cannot be written as a width 2 ABP, which is a formula, simple formula, but it cannot be expressed as width 2 ABP. On the other hand, it has an expression approximatively, right? This expression. So do induction on this, and so induction will now convert any formula to width 2 ABP approximatively. Okay, so that's it. So what you now know is, to reiterate, formula bar equals width to ABP bar, though formula is not. Yeah, so if this makes you happy, here is an example where approximative computation is more powerful, right? Although it doesn't make me happy because it's a very weak model. This width to ABP is a very weak model. It was actually, to begin with, it was incomplete. So approximative on top of this just makes it complete, but it doesn't really tell you whether at the level of circuits or formulas there are exponential gaps. So can you do much more with approximative computation than you could do with normal algebraic computation? Any questions? Okay.